WKB last time, and what I showed you was this. You have some hard differential equation to solve, which is this, which is really a Schrodinger equation. Okay, so Q, you should keep in mind, is V minus E. The Schrodinger equation is really minus y prime prime plus the potential, okay, is equal to EY. That's the time-independent Schrodinger equation. And put y double prime on the other side, and it reads y double prime is equal to V minus E, V of x minus E times y. And this is what we're calling Q, okay? So this is the equation that we need to solve. And one of the things that I pointed out is that the limit h bar goes to 0 is a very subtle limit. So, you know, when h bar is 0, this is supposed to be classical mechanics. When h bar is non-zero, that's quantum mechanics. But h bar is a dimensional quantity. Okay, so the limit h bar goes to 0 is very, very subtle. Okay, you can't actually take h bar to 0. Okay, because if you make it half as big, I'll just use different units, and it'll be twice as big. Okay, so taking it to 0 doesn't mean anything. Nevertheless, this is a differential equation, and we can put in a dimensionless number where h bar goes. Okay, and so what we're going to do is we're going to insert a small parameter here. And I emphasize this is a very, very strange thing to do. It's really strange, okay, because in the limit as epsilon goes to 0, this is no longer a differential equation. So the limit epsilon approaches 0 is a very, very singular limit, okay? And lots of work has been done on the classical limit of quantum mechanics, and I want to talk about that a bit today because it's so wonderful and so interesting. Okay, really interesting stuff. Just to give you a superficial picture of the connection between classical mechanics and quantum mechanics, suppose you have, suppose the potential is just, say, x squared, just quadratic well. So this is the harmonic oscillator, okay? So what we're talking about is a particle in a potential well, okay? So this is V of x, particle in this potential well. You give the particle a total amount of energy E, and you know perfectly well what happens classically. Classically, the particle goes back and forth. Okay? Quantum mechanically, however, the particle can tunnel a bit into the classically forbidden region. Okay? Now, in quantum mechanics, we are calculating this thing y, which is called a wave function, and the square of the wave function is supposed to represent the probability of finding the particle. It's actually the probability density of finding the particle. So the probability of a particle being in any region of space is y squared, okay? This is y squared dx is the probability of the particle being found somewhere between x and x plus dx. That's the probability of finding the particle in that little piece of space. You agree? Now, if you make a plot of classically of finding the particle, what is the, if we want to talk about the classical analog of that, what is the probability of finding the particle equal to? Where is it most likely that you would find the particle? Why is that? So it bends, so it's moving slowly out there. So it's much more likely that, if you close your eyes and you just reach out and grab the particle, it will be at the edge, okay? In fact, this is the reason there was this movie, this Rodney King episode. Any of you know who Rodney King was? Nobody remembers Rodney King. Rodney King was this, do you remember? Yeah, Rodney King was this guy on the West Coast, California, who was beaten up by the police, okay? And they were hitting him with a baton repeatedly. And the police got off. They were banging him on the head, okay? They caused brain damage. But when they showed the movie, what was happening was they were going down, the baton was bouncing off his head, and then it would come back up, and then it would go bounce off his head and come back up. And the most likely place to find the baton was up, because that's where it was moving slowly. So they showed the movie in court, frame by frame, and the baton was always up there. It was never on his head, so they got off. So the probability density, classically, of finding the particle is 1 over the velocity. The slower it goes, the greater the probability. So if you make a plot of the probability of finding the particle, it would be something like this. Probability would look like this. And in fact, it's infinite at this point. At this point, the probability is infinite. This is the classical probability. Be infinite over here and over here. That's the probability density. Of course, this is an integrable singularity. So the total probability, if you integrate the total probability, it still is equal to 1. Total probability of finding the particle somewhere is 1, but the probability density is infinite. Okay? On the other hand, if you look at the ground state, what does the ground state wave function look like? So the quantum, if I were to draw the quantum probability, P quantum, what would it look like? Well, for the ground state, it would look like this. It doesn't look anything like what the classical picture looks like. It's completely different. Okay? And this falls off exponentially, like that. However, as you go to higher energies, as the energy increases, the picture would look something like this. There's a dip, one node, and as you go to higher and higher energies, you have more and more oscillations, okay? And eventually, at very high energy, what you would see, the quantum probability would be something like this. So the classical probability has a strict cutoff, but the quantum probability begins to oscillate. There are nodes, of course. Chance of finding the particle in this state at this point is exactly 0. You'd never find the particle there, never. Okay? Classically, of course, you can find the particle. And there's an oscillation. So in some subtle sense, this oscillatory curve, as you go to higher and higher energies, becomes more and more like the classical picture. But this is really a very, very subtle difference. Okay, so quantum mechanics and classical mechanics, very different. Okay, now, because we're treating epsilon as small, in some funny sense, what we're doing is sort of halfway, when epsilon gets very small, halfway between quantum mechanics and classical mechanics, because we're treating the effect of h bar as being almost negligible. And that's why this is called the semi-classical approximation, halfway, halfway between quantum mechanics and classical mechanics. And what was the trick that we used? We said let y equal e to the 1 over epsilon, sum from n equals 0 to infinity, s sub n epsilon to the n. And what we found was that S0 is plus or minus the integral of the square root of q of t dt, plus or minus. Plus or minus because this is a second order equation and there are going to be two solutions. And we found that S1 was minus 1/4 log of q, okay? And Tibor, you did a tutorial and you got S2, right? People got S2. So S2 is, again, some sort of plus or minus something of an integral. Can you tell me what it is? What does S2 come out to be? Some function of q. What do you get for S2? What, say it again? 1 over 8 square root of 1 over 8 square root of okay, q double prime over q, yep. Q prime, okay, and is there some number here? It's something like 5? Good. Good, all right. So the question is this accurate? I mean, how do we measure the accuracy? And we, you calculate S3, S4. How accurate is this? Well, for example, what if we were solving the Airy equation, y prime prime equals xy? Okay? We put in an epsilon squared. So this is our perturbation parameter. We just insert an epsilon. Okay? Stick in an epsilon. Q, in this case, q of x, is just x. So the question is, how big is S2? That's the question. How big is S2? So S2, in this case, is plus or minus integral up to x, and you say it's 1 over 8 times the square root of t. This is the integral dt. All right? Now, q prime prime would be 0. Makes this a little simpler. Q prime is 1. This is q. So we get something like minus 5 over 4 t squared. Something like that. Okay? So this is minus or plus. The number is 5 over 32. 5 over 32 times the integral of dt over t to the 5 halves. And what is the integral of t to the 5 halves? It's t to the of 1 over t to the 5 halves. This is plus or minus 5 over 32, and it's t to the minus 3 halves times 2/3. Okay? So this is plus or minus 5 over 48, and this is evaluated at x, okay? So this is 5 over 48 x to the 3 halves. Okay? So the question is, how accurate is this? How accurate do we think this approximation is going to be if we just keep S0 and S1. Okay? If we're doing WKB theory, what is normally done in WKB theory, so y, which is e to the 1 over epsilon times that sum, what would it be? It would be e to the plus or minus 1 over epsilon times S0, okay, plus S1. Now, if we keep just this much of the approximation, this is the controlling factor of the asymptotic approximation. This is the controlling factor, and in the case of WKB, it has a name. This is called geometrical optics. And if you write down the full asymptotic approximation, including S1, that is called physical optics. Okay, geometrical optics means ray tracing. It's something that you do when you're studying elementary physics. And then there is an e to the S2 times epsilon, right? And you can approximate this by 1 plus epsilon S2. Okay? And this we would like to be small compared with 1 in order to justify using the physical optics WKB approximation. So the question is this small? Okay? That's the question. So, for example, suppose, say, x equals, I don't know, 10. Is this a good approximation? Well, if x equals 10, then 5 over 48 x to the 3 halves, what is that? That's 5 over 48. Now, 10 cubed is 1,000. And if I take the square root of 1,000, what is that? About 33 or something like that, right? So 33. Okay. Or 3 100ths. 15 over 48 is a third. So this is what? Roughly 1 over 300. So this is like a third of a percent. So that's the error. Oh, wait a minute. That's the error if epsilon equals 1. Okay? So if at the end of the calculation we said epsilon equals 1, the accuracy is a third of a percent. WKB is really good. Okay, we haven't tried to keep more terms in the WKB series. Look how accurate it is. That's pretty darn accurate. That's very impressive. Okay? So are there questions about that? So typically when we do WKB, this is all we do. And we hope that this term is small compared with 1. This is a third of a percent correction to 1 if epsilon is equal to 1. Okay, now of course, we typically are imagining epsilon to go to 0, like epsilon might be a tenth, because h bar is small. But never mind, we could set epsilon equal 1, because we're working in units where h bar is 1. And WKB is really accurate. Okay? So let me show you how powerful WKB is. Let's do a really, really hard problem. Not kidding, a really hard problem. How many of you know what a Sturm-Liouville problem is? What is a Sturm-Liouville problem? Do you know?
You have an eigenvalue equation and you find a basis or no basis, so you can solve the problem in that basis.
That's right. That's right. So Basically, a Sturm-Liouville problem is an eigenvalue problem. Okay? So let's write down a completely general Sturm-Liouville eigenvalue problem. Okay? So typical Sturm-Liouville eigenvalue problem would be, okay, Sturm Okay, Sturm-Liouville eigenvalue problem. It might have the form y prime prime plus q of x times y. Now notice this is plus q of x times y. And let's put in an eigenvalue. E times y is equal to 0. So this is the form of a Sturm-Liouville eigenvalue problem. Notice the eigenvalue multiplies q. So there's an eigenvalue in here. And q is some function. And the only, in order for this to be what is called a regular, we won't get fancy and talk about singular Sturm-Liouville eigenvalue problem. But a regular Sturm-Liouville, in a regular Sturm-Liouville eigenvalue problem, q is strictly positive, can never be equal to 0. If it's equal to 0, it becomes a singular Sturm-Liouville eigenvalue problem. And then what you said when you were, we need a boundary condition, right? So a simple boundary condition would be, say, y of 0 is equal to 0, and y of pi is equal to 0. So we can put the eigenvalue problem on the interval from 0 to pi. Okay, and I claim, I'm going to have to show you this, but I claim that, there's a whole theory. I can give you a course on Sturm-Liouville eigenvalue problems, interlacing of zeros of eigenfunctions and things like this. But basically, the kinds of things you should know are that the energies, or eigenvalues, E comes out to be a set of discrete numbers, eigenvalues E sub n, and corresponding to these numbers are eigenfunctions y sub n. Okay, and again, the eigenfunctions are required to vanish at 0 and vanish at pi. Okay? And furthermore, the eigenfunctions are orthogonal, and they form a complete basis, and you were saying that. So how do we show that the eigenfunctions are orthogonal? They are orthogonal, actually, with respect to the function q. Okay? How do we see that? Well, let's suppose we have an eigenfunction, y sub n of x. Then it satisfies the equation y sub n prime prime of x plus q of x times en times yn is equal to 0. Okay? And this is a very simple argument. Let's take this equation and multiply it on the left, or just multiply it, by y sub m. Okay? And then let's integrate from 0 to pi. Okay? So in the first term, I will integrate by parts. Now, when I integrate by parts, I have a boundary term, right? But do I get any contribution at the boundary? No, because y is required, all of the y's are required to vanish at 0 and at pi. So if I integrate by parts once, I get minus the integral from 0 to pi y m prime yn prime minus sign, right? So this first term becomes a negative term. And then I have plus the integral en times yn times ym times q, and that's equal to 0. Okay? And now I'm going to integrate by parts a second time. Let me raise this. Okay, let's integrate by parts another time. So now two derivatives will be on ym, and the sign will change to plus. So I have the integral from 0 to pi ym prime prime yn plus the integral en yn ym times q is equal to 0. But remember that ym prime prime is equal to minus q times em times ym. And therefore, if I combine these two integrals, it reads the integral from 0 to pi dx yn ym times q times en minus em is equal to 0. Now, if en is not equal to em, then this is not 0, and therefore the integral, therefore it follows that the integral of q times yn times ym is equal to 0. And you were saying the word orthogonal, and that's the proof of orthogonality. Okay? So this is an example of one of the theoretical results. But come on, we're physicists. We want to know the answer. What is the eigenfunction? And what is the eigenvalue? We want to know. Okay, how are we going to find out the answer? Well, let's assume that the eigenvalue, let's just make a funny assumption. Let's assume that En is pretty big. Okay, let's just make that assumption. Okay, so let's just put this a little higher up. Let's assume that the eigenvalue E is pretty large. And therefore, I will say that I'll just make a substitution. Let's call E 1 over epsilon squared. Okay? Okay, everybody? I'm just going to define E to be 1 over epsilon squared. Then the Sturm-Liouville problem reads epsilon squared times y prime prime plus q times y is equal to 0. Now let's think of epsilon as being small because E is pretty big. How do we solve this problem using WKB? Well, the only change is that Q here, where's the pointer? The only change is that Q over here is the negative of the Q that we were talking about with generic WKB. Since we're replacing Q by minus Q, then in this WKB approximation here, there's a factor of I. But you notice that there are two solutions. There's a plus I and a minus I. Can we go? Can't go a little higher. Okay, so there's going to be a plus I and a minus I. Now, e to the plus or minus I, a linear combination of e to the plus or minus I times something, can be written as also a linear combination of sine and cosine. Do you agree? So therefore, I could write down the WKB approximation this way. I could say that for that y of x is asymptotic to either a sine of 1 over the square 1 over epsilon integral of the square root of q or the cosine of 1 over epsilon integral dt square root of q of t. And this is divided by q to the 1/4 of x. This is divided by q to the 1/4 of x. And there's an arbitrary constant here, call it a. There's an arbitrary constant here, call it b. So this is the WKB approximation, and the only thing I've done is I've replaced q by minus q. Okay? Any questions about that? You see what I've done? Yeah. Yeah. So e to the log of q is 1 over q to the 1/4. 1 over q to the 1/4. Now, obviously, if q becomes negative, then there's a factor of minus 1 to the 1/4. But that's absorbed into this constant. Okay, so I'm only dealing here with real positive quantities. And I've taken all of the complex stuff and stuck it in here and here. Okay? And these constants are arbitrary because it's a linear equation, linear homogeneous equation. Okay, now there's only one last thing. To make this approximation non-ambiguous, we need to know what the lower endpoint of integration is. And a natural lower endpoint of integration to choose is 0. If I choose a different lower endpoint, then I would have to adjust the constant a and b, but it's the same approximation. There you go. That's what WKB says. This is the solution. This is asymptotic to y as epsilon goes to 0. But remember that y of 0 is that we have a boundary condition that y of 0 equals 0. What does that say? What does that imply? That b is 0. Okay? That just tells me this implies that b is 0. So therefore, this term is in fact not here. Now we have another boundary condition. We have the boundary condition that y of pi is 0. Okay? What does that tell me? Well, if you plug in pi, this gives me so y of pi is a over q to the 1/4 of pi, whatever that is, times the sine of 1 over epsilon integral from 0 to pi dt square root of q of t. And this guy has to be 0. How can that be 0? Yeah. Apparently, for very special choices of epsilon, the only way this can be 0, remember, this is a positive number. A is some constant. And the only way this can be 0 is for this thing inside to be a multiple of n pi. A multiple of pi, n times pi, an integer multiple of pi. So therefore, I conclude that 1 over epsilon times the integral from 0 to pi dt square root of q of t is equal to n pi, n equals 1, 2, 3, 4, and so on. Okay? That's very interesting. So all I need to do is to square this equation. Let's just square this. And if I square it, what do I get for 1 over epsilon squared? Well, we just said, let's call 1 over epsilon squared. We said 1 over epsilon squared is e. So if I square this equation, I get e is equal to n squared pi squared over the integral from 0 to pi dt square root of q of t squared. Okay? And that is a formula for the nth eigenvalue. Now, of course, this is not an equal sign. This is really an asymptotic sign. And this is valid when e is large compared with 1. That means as n goes to infinity. So we have a formula. I mean, do you realize what we did? We just solved all possible regular Sturm-Liouville eigenvalue problems. Right there. There's the eigenfunction. There's the eigenvalue. And we have shown that the eigenvalues of a Sturm-Liouville eigenvalue problem grow like n squared. That's what we showed. I hope you're impressed. Do you see how powerful we are? Do you also see that by doing perturbation theory, we are doing global analysis? Because do you see what we did? We imposed one boundary condition at y equals 0 and one boundary condition at y equals pi. Widely separated boundary conditions. You see that? We're not doing a Taylor series about 0 and hoping it's good at pi or something like that. We did a global approximation which is valid for small epsilon everywhere. And that's the answer. Now, of course, I know what you're thinking. How accurate is that? Okay, I'll show you. Okay, so I took, okay, so I took this to be q. Okay, just some funny function. I took x plus pi to the 4th power. I just took that because I want to make a really difficult differential equation to solve. Okay, you're not going to solve that differential equation. So in this case, I chose, let's write it down, I chose q is equal to x plus pi to the 4th power. Some silly function, okay? Now, how accurate is our approximation? Well, when n is equal to 1, now remember, our approximation is valid as n goes to infinity. When n is equal to 1, our WKB approximation for the eigenvalue comes out to be, here's the nth eigenvalue from WKB. Here's the nth eigenvalue, the exact answer. And the relative error is 8.1%. Okay? And when n is equal to 2, the relative error is 2.6%. And when n is equal to 3, the relative error is 1.3%. And by the time you get to the 10th eigenvalue, the error is 0.13%. Okay? So you can see as n increases that the error goes down. Furthermore, you might be interested in looking at the eigenfunctions. So this is the WKB approximation to the eigenfunction. And this is what you get if you simply integrate it exactly on a computer. And you can see the difference when n is equal to 1. Okay? Remember I showed you in quantum mechanics, as you go to higher and higher energies, you develop nodes in the eigenfunctions. But for the ground state here, there's no nodes. Okay? Yeah?
So your potential in some x without 4 times yeah,
Right, but this is not in the form of a Schrödinger equation where the energy is separate. This is a regular Sturm-Liouville eigenvalue problem.
I'm wondering if the wave function, how realistic is it that the wave function is becomes 0 at a finite value of x? Or would it work if the wave function kind of went in 0 at infinity?
Oh, we have to talk about that. That's the real impressive calculation for WKB. That's what I'm going to be showing. That's the objective. That's where I'm heading for in this course. We got to the end of this problem quickly, and that's a subtle. That's going to take more than a lecture just to answer that question. Okay, but notice that the error is almost invisible. Yeah.
The second boundary condition, when we applied the second boundary condition, we didn't determine the arbitrary constant A.
We didn't determine the constant because it's a homogeneous equation. Okay? The equation is a homogeneous equation, but let me answer your question. You always ask interesting questions, so let me show you how you answer that question. You'll love this. Okay? How do we calculate A? How would you calculate A? Well, you need a normalization condition, right? So a typical normalization condition would be that the integral from 0 to pi dx times yn squared is 1. The square of the probability integrated from 0 to 1 is 1. That's how we're going to normalize. Okay? Sorry? Q. Thank you very much. Yes. Times Q. Thank you very much. I'm glad you said that. Otherwise, we'd have a disaster. Okay. So can we do this integral? Let's see if we can do the integral. Okay? So that's the integral from 0 to pi dx q of x. And now, what is y squared? Y squared is a squared over the square root of q, right? I'm squaring it, so the fourth root squared is the square root, times sine squared of 1 over epsilon, integral from 0 to x, dt, square root of q of t. Okay, that's the integral we have to calculate. Got it? That's interesting. Look, the square root of q divides into q to give me the square root of q. This looks like a very hard integral because it's an integral of the square of a function containing an integral. Ugh. Can we do this integral? Yes, we can. Okay, this is required to be 1. Okay? Can we do this? Yes. Let's do the following. Over here, let's call this a new variable. Okay? In fact, let's call this z, say. Z is equal to 1 over epsilon, integral from 0 to x dt, square root of q of t. Okay? Why should we do that? Because dz is 1 over epsilon times the square root of q of x dx. Ooh. Okay? And furthermore, at x equals 0, z is equal to 0, right? If you said x equals 0, z equals 0. And at x equals pi, z is equal to 1 over epsilon integral from 0 to pi times dt times square root of q. But what is that equal to? What is this? 1 over epsilon integral from 0 to pi. What is that? N pi. Right, that's just n pi. Therefore, if I just divide this by epsilon and multiply by epsilon, you notice over here I have dx times 1 over epsilon times the square root of q. Therefore, this integral I'm trying to evaluate is epsilon a squared times an integral from 0 to n pi, right, dz sine squared of z. That's it. And that's supposed to be equal to 1. What is the integral from 0 to n pi? Well, it's n times the integral from 0 to pi, because it's periodic. And what is the integral from 0 to pi of sine squared?
Half?
It's,
Maybe a quarter.
it's a half pi, 1/2 pi, okay? So this is epsilon a squared times 1/2 pi times n. And that's equal to 1. And that's the formula for a squared. Okay, so we normalized it. So that's the answer to your question. Okay? So look how accurate that is. But this is the most inaccurate part of our approximation. It's n equals 1. What about n equals 2? So for n equals 2, the picture looks like this. And now you can barely see the difference. Okay? This is the WKB approximation. Here is the exact solution. And if you look very, very carefully, you see the line looks a little bit thick over here. Okay? And it looks a little bit thick over here. But in this picture, you can't resolve the difference. Do you see how fantastic asymptotics is? We just solved the arbitrary Sturm-Liouville eigenvalue problem for all Sturm-Liouville problems, just like that. Okay? And we can normalize it, we can check orthogonality, we can do all of these things. Okay? Yeah?
Is there like a good reason why the approximation is better, like where the derivative is smaller?
Yeah, it has to do, well, I mean, you can verify this by calculating S2. Remember, in our, in what we just did, we said we would like to solve this just using the physical optics approximation. You understand, we could have done a much, much better job, but we're lazy. Okay, we're very lazy today. We could have included S2, S3, S4, and S5. Okay, but I'm not an undergraduate student, so I'm too lazy to do that. Okay, but, you know, and if you're a graduate student, you'd probably go up to S3. Okay, so, but the answer to your question is that we can predict that the line should be thickened here and here because you can calculate the error, just the way we did before, earlier today. We said the error was 1/3%. We can ask, when does S2 get biggest? And that's where S2 is biggest. It's a measure of the error. WKB comes with its own error prediction. It's wonderful. So you know where it's not going to be so good. Okay, now, so we're feeling very powerful. But there's a problem. Because we are not just mathematicians solving Sturm-Liouville eigenvalue problems. We're physicists. And we would like to solve a problem like this. Y prime prime is equal to Q of x times y, where Q is equal to V minus E. Okay, and we're going to put in an epsilon squared over here. But now we're not solving a regular Sturm-Liouville eigenvalue problem. We're going to solve an eigenvalue problem which is singular. Okay? In what sense is it singular? It's singular because we are going to impose boundary conditions not at 0 and 1, but as you know, we're going to require that y of minus infinity is equal to 0 and y of plus infinity is equal to 0. This is the problem we want to solve. And I'm going to show you how you use WKB to solve this problem. And this is something you never learn in classes on WKB because there are very few people who can actually do this on the board, okay? So that's what we're going to do. And this is so beautiful. This is what I'm going to show you is, I think, one of the great breakthroughs in asymptotics and perturbation theory of the last century. absolutely an astonishing calculation. Okay? And I want to show you why the problem is non-trivial. Okay? Why is the problem non-trivial? The problem is non-trivial. You understand what I would like to do. Okay? All I need to do is to say that y is equal to e to the plus or minus integral up to x of the square root of q of t dt, okay, times 1 over epsilon over q to the 1/4. That's the WKB approximation. And so you know what I want to do. All I want to do is to say it's a times the thing with the plus sign plus b times the thing with the minus sign. There you go. And I'm going to impose these two boundary conditions, and I'll be done. This is a plus sign. Yeah, and this is some approximation, okay, as epsilon goes to 0. But I'm making this approximation. I require that it vanish at minus infinity, it vanish at plus infinity. It looks like Bob's your uncle. Do you know the expression, Bob's your uncle? It means everything works. Okay. The equivalent is Matilda's your aunt. Okay. Okay. So it looks perfect. There's only one problem. WKB is not valid for all x. Why not? When is WKB not valid? Right. Okay? When, so this is no good when Q is equal to 0. Why not? Well, this is 0, and WKB is blowing up. But wait a minute. Why is that bad? Why is it bad that WKB should be blowing up? What's so bad about that? Well, so it blows up. So maybe the actual solution to this equation blows up. But it doesn't blow up because if Q is some polynomial, some analytic function or something, some smooth function, we know that the solution to this differential equation definitely does not blow up. There's no singularity in this differential equation except in infinity, and yet the WKB approximation is blowing up when Q equals 0. When is Q equals 0? I've already talked about that in class. Q is equal to 0 when at that turning point, okay, when V is equal to E. So I would like to spend a little bit of time today talking about the nature of turning points, because this in itself is fascinating. It's absolutely fascinating. And I really love this stuff. Okay, so what's so cool about it? What I want to talk to you about is what happens when V is equal to E. So again, here's the problem. You've got a potential. Okay, there's some sort of potential here. This is V of x. You have a particle of energy E. Okay, and what is this? This is the total energy. E means total energy of the particle, kinetic plus potential. So what happens? The particle is moving along, classically. As it goes closer and closer and closer to this point here, where V is equal to E, what happens? More and more and more energy of the particle becomes potential, less and less becomes kinetic, and when it reaches this point, it has no kinetic energy left. That is, this much is the potential, and this much is the kinetic energy. This is the potential. This is the kinetic. This is the total energy, E. And as it goes closer and closer to the turning point, it's going slower and slower. And it stops. And it turns around and goes back again. In fact, You've learned this in your first year undergraduate physics class. What you learned, so in first year undergraduate physics, your teacher said, today we're going to talk about the harmonic oscillator and Hooke's law. And you learned that the Hamiltonian for the harmonic oscillator is p squared plus x squared. That's the energy of the harmonic oscillator, right? And you learned that the energy is conserved. Okay, so this says that the square of the speed plus the square of the position is a constant. It's equal to the energy. Okay? And this is what your teacher said. Your teacher said, the turning point occurs when p is equal to 0. When p is equal to 0, that tells me that x squared is e, or that x is plus or minus the square root of e, right? And so therefore, this is x. Here is x equals 0. Here is the square root of e. Here is minus the square root of e. Which way is the force? The force is the negative derivative of the potential. So it's minus x, or in this case, minus 2x, right? So the force is toward the origin. The force is this way, toward the origin. So a particle is traveling along. The force is acting this way, so the particle is slowing down. Or to think of it in energy terms, it has less and less kinetic energy. It goes all the way out to here. It stops, turns around. That's why this is called a turning point. Goes back the other way, goes faster and faster and faster. The speed is maximum at x equals 0. It keeps going to here, turns around, goes back again, and goes back and forth. And that is the end of the lecture. I mean, what else can you say in freshman physics? Okay, that's it. After the class, a very bright undergraduate student comes up to the professor and says, you said to us that the particle is executing simple harmonic motion. It's going back and forth like this. And this equation here says if I know where the particle is, if I know x, then I can solve this equation, and I know p. So if I know where the particle is, I know how fast it's going. Right? So if you're here, I know what the velocity is because I know the kinetic energy. Okay? Of course, up to a plus or minus sign. It could be going that way or that way. But what about the can't we start the particle off, say, over here? Okay. The professor looks at you in horror and he says, you're a moron. No, he never says that. I promise, he never says that, okay? In professor school, they teach you never to talk like that to undergraduate students. Okay, the professor smiles in a very condescending fashion, and he says to the student, well, you see, you can't have the particle over there because this is called the classically forbidden region. This is the classically forbidden region. This is the classically allowed region, but you can't be in the classically forbidden region because if you were over there, x would be greater than the square root of e. And therefore, x squared is greater than e. But if x squared is greater than e, and p squared plus x squared equals e, then that tells me that p squared is negative. How could p squared be negative? Okay, it's a square. It can't be negative. So the professor is very satisfied with himself. And the student says, what do you mean p squared? Why can't p squared be negative? It could be negative. Why not? We'll just draw a line like this. We'll call this the complex plane. And the velocity at this point is pure imaginary. What's wrong with that? So the particle's going that way in the imaginary direction. Okay? So we can solve, so this is the complex x-plane. And we can ask, if you start the particle over there, where does it go? Okay? We can plot x of e because, remember, we're solving the equation f equals ma. That is the equation x dot dot plus x is equal to 0. That's, just f equals ma, right? Or if you want to be fancy, you take this equation, and what we're solving is p squared, well, p is equal to the square root of e minus x squared, and p is dx dt. So it's just a first-order differential equation. So we can do that. It's not a big deal. And if you solve that differential equation, subject to this initial condition, where does the particle go? Well, it goes like this. Okay, and it makes an ellipse. This is an exact ellipse, not an approximate ellipse, but it's an exact ellipse. And it turns out that, see, there was no pun unintended there. It turns out that the turning points are the foci of the ellipse. Okay, this is elementary physics extended into the complex plane. This is complex classical mechanics. And the particle goes around like this. And you can see that it's perfectly acceptable for a particle to be in the classically forbidden region. But if it is in the classically forbidden region, which way is it going? It's going that way. It's going in the imaginary direction. So why is it that a classical particle cannot tunnel? It's because it's not going the right way. In the classically allowed region, on the real axis between the turning points, it's going parallel to the x-axis, but here it's going perpendicular to the x-axis. So it's not penetrating into the classically forbidden region. But can a particle be there? Yes. And in fact, the amount of time it takes to go back and forth like this, so we have here a whole family of ellipses, nested ellipses, and the time it takes for the particle to go around any ellipse is always the same. Why is that? By Cauchy's theorem. The time, the period, is the integral dt around a closed loop. But dt is equal to dx over p, which is equal to dx over the square root of e minus x squared. And the only singularity is a branch cut right there. So the integral is always the same. You can deform this from one path to any other path, and t is the total time of transit is always the same. By the way, you notice that the force is the negative derivative of the potential. So the force on the real axis is this way and this way, as I said before. But on the imaginary axis, the force is, on the imaginary axis, x squared, the potential, becomes minus y squared, changes sign. So the force is that way and that way. It's away from the origin. So why doesn't the particle just fall off to infinity? Why does it go around in a closed loop? Why doesn't it just get sucked off to infinity? The answer is the same as the reason that we don't die. Why don't we die? Why don't we die right away? That is, why doesn't the Earth fall into the sun? There's an unbalanced force, right? Here's the sun. Here's the Earth. It's going around the sun. The only force on the Earth is gravity, pulling it toward the sun. Why don't we die? Why don't we fall into the sun and die? The answer is, we are falling into the sun. We're in free fall. However, lucky for us, we're not getting any closer. We are falling around the sun. We're always falling. We're always falling into the sun. If we weren't falling into the sun, we wouldn't go that way, we would go that way. So we are falling into the sun. We're just not getting any closer. This is indeed a particle that's falling off toward infinity. It's just not getting any closer. Okay? That's all. So we have here a complex atom. And when you quantize the complex atom, what are we really doing? We are saying that there are an integral number of wavelengths plus a phase shift from going around in the circle, and there should be n of them because a particle is a wave. That's the reason why the harmonic oscillator has quantized energies, okay? But the point is, don't be so narrow-minded. Why is it that in freshman physics, the only solution to F equals ma they teach you is this, and they say it's going back and forth? Wrong! It's not going back and forth. It's a degenerate ellipse. It's really doing this. It's going infinitesimally above the branch cut, going around the turning point, and going infinitesimally below the branch cut like this. It's making a loop. It's not going back and forth. It's going around and around in the complex plane. Okay? Now, it's actually kind of interesting because I'd like to show you, maybe I can show you a movie. Let's see. Let's see if I can show you. Okay, so I want to show you a movie of how this actually looks. Okay, so this, I mean, you can have undergraduates play these games, but this is really fun. Okay. See, can we make this big? I think we can. Yeah. Okay. Okay, so that is the real axis, in case you don't remember. I'm emphasizing that. And here is the harmonic oscillator, and the particle is going back and forth. And here is the turning point. I put the turning point at 1, okay? And I say to myself, let's start the particle over there. And then I say, well, wait a minute, this will never work because that's in a classically forbidden region. But if you solve the differential equation, you remember that's the imaginary axis, what you see is the particle goes like that. And if you take a whole bunch of particles, you notice they always take the same amount of time to go around, always. And in fact, you can do something very interesting. One of my interests is to start, and this is a question that was asked in class by, who asked it? One of you guys asked it. Maybe you asked it? Somebody asked it. You said, what happens if you put the small parameter in the exponent? Which of you? Early on. Yeah, maybe you asked it. Yeah, you're guilty. Okay. So suppose we take the harmonic oscillator, but now we put a small parameter in the exponent. And we ask, what happens if epsilon begins to increase? Okay? Let's ask, what happens if epsilon begins to increase? So, for example, what happens if epsilon is equal to 1? This is an I over here, which is very interesting, and I'm not going to explain why it's there. But suppose we take epsilon equals 1, then we get, instead of the harmonic oscillator, we get the Schmarmonic oscillator, or something like that, and it reads Ix cubed. Now what happens? Well, as epsilon increases, those two turning points over here move downward into the complex plane over here. But if you start a particle at this turning point, what does it do? It goes back and forth like this. And if you start the particle somewhere else, it goes around like this. So these are just deformed versions of those ellipses, these ellipses here. So let me show you what I mean. let's see. I think we have to do this. Okay, here's epsilon equals 1. Here are the turning points, and you see that it always takes the particles the same amount of time to go around, and that's the picture that you get. Okay, so this is a deformed version. Okay, it's very interesting. In fact, things get even more interesting, because what happens if you take epsilon equals 1/2? Now, the x-plane, the complex x-plane that they're moving in, has a branch cut. And the particles can go through the branch cut. So there are several sheets, so they can travel around. It's still an oscillator, but they can travel around and make knots, traveling around on different sheets of the complex plane. Hang on for just 1 second. So let me show you. So here's epsilon equals 1/2, and the particle is making this beautiful picture like this. There's a turning point here and here, and it looks like the path is crossing itself, but it isn't, because there's a branch cut here, and the particle crosses the branch cut, goes around on the second sheet, crosses back again, and goes back on the first sheet. Okay, and it goes back and forth like this on 2 different sheets of a Riemann surface. Okay. In fact, now let's see. You had a question.
I'm not sure if it's relevant, but if you consider some kind of relativistic harmonic oscillator, we had a limiting. Would that mean that you would have if you started off from the classical trajectory?
This is an interesting question. This is an interesting question, but let's talk about this afterward, because this is a very interesting question. Okay, that's really interesting, but it's a long discussion. But I agree with you; it's a very interesting question. Okay, so we're just considering not relativistic mechanics, but just F equals ma, non-relativistic. Okay. You could even do super relativistic. Okay, remember what Einstein said about traveling faster than light. This is very relevant today with some experiments going on, right? Einstein said that you can travel faster than light. It's perfectly acceptable mathematically. The problem is that if you do, you lose your luggage. That's the problem. But this is just non-relativistic, okay? So, okay, so how about a different value of epsilon? Let's try epsilon equals 10/9. And I want you to see what the trajectory looks like. I say we better fast forward this. And this is what the trajectory looks like. This is a closed orbit, and you can quantize it. And this visits 11 sheets of a Riemann surface. Is that beautiful or what? This trajectory never crosses itself. It's periodic motion. Okay? In fact, we can make a monster here. Okay? So the monster is, instead of taking epsilon equals 10/9 over here, I took epsilon to be 16/15. And you're going to see a monster. Okay, this is really wild. So here's 16/15, and the particle takes off, and I say, this is a really cool one. Okay, and it's going along and traveling through the complex plane and crossing the branch cut. I say, but this is going to take a long time because the orbit hasn't closed yet. And it's going and going, and I'm getting bored. So I'm going to super fast forward this, and now you're going to see why it's called the monster. Okay? Now, if you look very carefully, you'll see a smile over here. Okay? And you'll see 2 eyes and a nose and whiskers. Okay? And this is the complex plane. This is the trajectory that it made in the complex plane. Absolutely Wonderful. This is just F equals ma. And here we're coming back. And here are the two eyes and the nose and the smile. It's just off the edge over here. Okay? And these trajectories do not cross. This is periodic motion. This is an oscillator. It's a complex oscillator with periodic motion in the complex plane. Okay? This is just what you get when you deform into the complex plane some of these lovely little innocent ellipses. Okay? It's really cool stuff. Yeah.
How many sheets appear?
There are, in this one, I believe they're on the order of about 20. Okay, it's a small number. I mean, and depending on your initial conditions, you can visit huge numbers of sheets. You could, in principle, visit, you know, an arbitrarily large number of sheets. If it were an infinite number of sheets, however, it would be chaotic. Okay, so it's a finite number, and the orbit closes. Okay, but let me just conclude before, because I don't want to. I want to just say something really cool. You see, in all of these pictures, the orbit closes. And that's because the energy is real, turns out. If we allow the energy to be complex, then the orbit in general won't close. Okay? It doesn't have to close. So let me give you an example. Suppose we have the potential, let's see, let's take the potential x to the fourth minus x squared. Just x to the fourth minus x squared. Okay? Let's draw a picture of that potential. So this is v, this is x. Okay? When x is equal to 0, it's 0. Then it goes downward, because this is negative. And then it turns around and goes upward. And now let's put a particle in the potential well. You notice there are 4 turning points, classically. This is just classical, first-year undergraduate classical mechanics. So what is happening? Well, there is, on the x-axis, there are 4 turning points. If you put a particle in this well, it goes back and forth. If you put a particle in this well, it goes back and forth. Do you agree? That's all it can do. And it can never get from this well to this well because it would have to tunnel. And that can only happen in quantum mechanics. Right? Well, if we draw the complex plane, here are the turning points in the complex plane. If you put a particle here, it goes back and forth. If you put a particle here, just outside in the classically forbidden region, it goes around like this. Those are the little ellipses. Here it goes around like this. And as you go further away, it begins to look triangular. It comes around like this, and goes out, and then it comes around like this, and goes out. In the complex plane, like that. And you notice that the particle on one side can never travel, even in the complex plane, to the other side, because in classical mechanics, there's no tunneling. But quantum mechanics says that when you measure the energy, you can't measure it exactly because of the time-energy uncertainty principle. Okay? Unless you have an infinite amount of time, there's always going to be an error. There's always going to be an error in your measurement of the energy. What happens if the error is, say, a small imaginary number or a small complex number? What happens now? Okay? So what happens now, here are the turning points. Let's let the energy be equal to some number like 6 or whatever you like it to be, plus a little bit of complex. Now the orbits are no longer closed. And what you see is something like this. You start a particle in this well, and it goes like this, and it doesn't close, and it goes out, and eventually it crosses the imaginary axis. And you would think that now it goes off to infinity, but it doesn't. What it does is it spirals into this well, crosses the x-axis, the real axis, comes back out, never crossing itself, because this is a deterministic system, so it can't cross itself. Goes all the way out and goes into this well. And in fact, it tunnels back and forth. And if you ask how long it takes to tunnel, the tunneling time, the amount of time that it before it crosses the imaginary axis and goes into the other well, the amount of time it takes is inversely proportional to the imaginary part of the energy. Time times energy is a constant. Classical mechanics knows all about the uncertainty principle, energy times time. Okay? And I thought I would show you, just before we quit, let's see. I think I have. Okay, so this is that quartic well, and this is what the particle is doing. Okay, it spirals out, it crosses the imaginary axis, comes like this, goes in, and then it comes back out, never crossing itself, crosses the axis, and so now here it's going to replay, so you can see it makes a great big loop here. It's not going off to infinity. It goes in, goes back out again. The red dots are the turning points. It spirals all the way in, and then spirals back out again. So if you ask, what's the connection between classical mechanics and quantum mechanics? Classical mechanics, F equals ma, can exhibit tunneling. The particle can go from one well to the other, but the only way it can get from one well to the other is for the particle to go through the complex plane. It can't go there on the real axis. Okay? In fact, in quantum mechanics, what do you observe in a quantum experiment? You can do quantum tunneling experiments. You have a barrier, and an electron enters the barrier and it comes out the other side. What path did it take? Well, you're not allowed to ask that question in quantum mechanics. In the classically forbidden region, you can't talk about the particle trajectory. I would argue that the particle actually went through the complex plane. Okay? In fact, classical mechanics and quantum mechanics are a lot closer than you might have thought. If someone said to you, what's the difference between classical mechanics and quantum mechanics? You would say, well, come on, quantum mechanics allows for tunneling, virtual particles. Classical mechanics doesn't allow for such exotic phenomena as tunneling. You know, throw a ball against a wall and it goes through the wall, et cetera, et cetera. Okay? No, you can do this in classical mechanics. All you have to do is generalize classical mechanics to the complex plane, and you can see the particle going from one well to the other well. Okay? Yeah?
Can you predict a number that is measured in quantum mechanics by doing classical mechanics and quantum mechanics?
Yes. So what we can do is we can ask, so we have to be very careful because we don't want h bar to get in the way. There's no h bar in classical mechanics. But we can ask the following question. This is a paper I just published a few months ago. Okay? You can ask the following elegant, I think it's a really cool question. You can say, in quantum mechanics, if you have an unequal, an asymmetric double well, you know, let's take a double well like this, say an asymmetric double well. You can ask, in quantum mechanics, what percentage of the time is the particle in this well and what percentage of the time is in that well? So now you get a pure number. It's just 36% here, 49%, you know, that kind of thing. Just a pure number. Okay, so the number, I'm not asking for a tunneling which involves h bar, but just a ratio of time. Now, I can take this same problem classically, give the particle an imaginary energy, and answer the question. Now, as epsilon, if epsilon is equal to 0, the particle is never going to tunnel. It always stays on one side or the other. But in the limit as epsilon goes to 0, okay, we can calculate that ratio classically, and it has a well-defined limit. And when epsilon finally goes to 0 and the energy of the particle is real, what survives is that ratio, the ratio of the time spent on one side compared with the other side. And that turns out to be very close to the quantum answer. Okay, but not exactly the same. It's quite close. But classical mechanics has a lot of the quantum behavior that you might expect. Okay, classical mechanics is very rich. Okay, so you know they give you a throwaway course when you're an undergraduate classical mechanics, the sophomore, you know, and then you forget all about it. Oh, it's really interesting. Classical mechanics is really fascinating stuff. Has a lot of the features of quantum mechanics. Okay, if you're interested.